Welcome to section 7.6 on covariance, variance, and correlation. The goal of this section is to calculate the covariance and correlation of two random variables and to study the properties of covariance and variance. 7.6.1 Definition of covariance. In order to understand the definition of the covariance of two random variables, it's useful to recall the definition of the variance of a single random variable, and that's definition 7.6.1. The variance of a random variable x is v of x, and it is the expected value of x minus mu sub x squared, where mu sub x is the mean or expected value of x. And this can be calculated using Lotus in one of two different ways, either whether x is discrete or continuous. If x is discrete, then we're summing over all x, the same x minus its mean squared times the probability mass function, p of x. And if x is continuous, then we're integrating over all possible values of, again, x minus its mean squared times the density function, f of x dx. So p of x is the pmf, and f of x is the pdf of x. And so the remark is that the variance is typically the nicest measure of the average distance. There's other ways of measuring that distance, but the variance is the average or the expected distance. So distance is the x value minus its mean. That's how far any given x value is away from the mean. Definition 7.6.2, the covariance of two jointly distributed random variables x and y is covariance of x is again an expected value. This time it's expected value of x minus its mean times y minus its mean. And this, so what do we have here? Mu sub x is the expected value of x, and mu sub y is the expected value of y. And again, using Lotus, there's two different ways of calculating this depending if they are discrete, the two random variables, or if x and y are continuous. If x and y are discrete, then we're summing over all x and all y of this product, x minus mu sub x, y minus mu sub y times the joint mass function, p of xy. And if they are continuous, then we're integrating over all possible values of x and y. Again, this product, x minus its mean, y minus its mean, times the density, the joint density, f of xy and dy dx. Dx dy doesn't matter if x and y are continuous. So what do we have is p of xy is the joint pmf, and f of xy is the joint pdf. So before we go and dig into this definition to interpret what it means in terms of the relationship between the variables x and y, we're going to look at two little properties of the covariance that follow very quickly from the definition. And that's proposition 7.6.1. Let x and y be two jointly distributed random variables. Then the covariance of yx is equal to the covariance of xy. So it is symmetric, and so we can see that by just looking at this product. So we have the covariance of yx, so the covariance of yx, if we keep the order that we have in the definition, that's y minus its mean and x minus its mean, and this inside the expected value, that's just a multiplication. That's just a multiplication, and so we can reverse the order of that very easily. So that's the expected value of x minus its mean and y minus its mean, and that is the definition of the covariance of x, y in that order. Next, the covariance of x with itself. The covariance of x with itself is the variance of x, and you can see that as well here. If you can imagine replacing the second variable with the same term, then you're going to get the definition of the variance up here. So let's write that down formally. The covariance of x and x is the expected value of the first variable minus its mean times the second variable, which incidentally is the same, times its mean. Well, this is the same thing twice, so that is the expected value of x minus its mean squared, and that is the definition of the variance. In the next video, we will look at the covariance from a graphical standpoint and interpret it in terms of what it can tell us about the relationship between variables x and y. See you then.